Hello, everybody. Welcome to class. I know we're a little early, but I'm glad you're here. So if you want to say hi in the chat, I would appreciate that because I like to see who's here. James is back, going for the double today, linear algebra and then calc. Turner, Jared, Jax. Hello. Lauren, good morning. Felipe, hi, welcome to the stream. We're going to be doing a little test review today. So anywhere between implicit differentiation and related rates, curve sketching, mean value theorem, any of that kind of stuff. Logan, hey, glad you're here. How many subscribers until we see the full collection of Hawaiian shirts? Well, if this what is this called? Lockdown, stay at home order, whatever it's called, stay in place order continues, you'll see them by the end of the semester, I'm sure. This one's pretty nice though. It's got an airplane on it, a house. All right, well, it's 10 o'clock. So if anybody's prepared for the April Fool's Day edition of the simultaneous SIP, feel free to join. It's good as always. Let me know in the chat who joined in the SIP. But the plan for today is, yes, a lot of SIPs today. My linear class was lacking with the, they're going to be able to see this because it's going to be published. But yeah, nobody did the SIP today. This class, 10 SIPs at least, or 9. Okay, so the plan for today is I have nothing prepared. We're just going to work on the review sheet. So basically, I guess since I can't have you raise your hands, it's just going to be kind of comment in the chat what question you want us to work on. I would prefer not to do one of the first 7 because we did that yesterday during the live office hours. So those are on YouTube already. So if you want to just check those out. Isabella says 11. She was first to it, so we'll start with 11. It is possible. There's one question. Jack says 11. Okay, before we get to 11, is the issue that I had a typo in the answer key? But it seems like most people are happy with 11 either way. So we could start with 11. Yeah, so you had a pi squared in the denominator, I'm assuming? I'll fix the answer key. Yeah, there's a typo in the answer key for 11. Should we still do 11? Okay, yeah, let's just do 11. Okay. let me find the question. Okay, so the area, the circumference of a sphere is measured to be 84 centimeters with a possible error of 0.5 centimeters. Okay, use differentials to estimate the maximum error in the calculated surface area. Okay, so what we want to do is we want to express the surface area of the sphere in terms of its circumference. How do we do that? Anybody have any ideas? Well, while the ideas trickle in, the surface area of a circle is given by A equals let's see what we have. Yeah, well, I'll tell you. So this is what you should know from high school geometry, that the surface area is equal to 4 pi r squared. But we want to express it in terms of the circumference. So yeah, could you get the radius value from the circumference? We could. How about let's just solve. So the circumference of a circle we can solve for r and then plug that into the area function, and that gives us a way to express the area in terms of the circumference. Right? And the reason why I don't want to solve for the radius in terms of, solve for r in terms of this information is our possible error is from the circumference. It's not from the radius. So we'd have to switch we'd have to figure out what our radius error is as well. Okay, so I think it's easiest if we just say, well, r is equal to c over 2 pi, and then we plug that into here. Okay, so really A we could express as 4 pi times c over 2 pi squared. Yeah, Isabella, what you wrote is also true, but then we're going to have two variables, right? And then it could get a little bit messy. So I think it's just easiest to, we have this formula for area in terms of the radius. Let's just rewrite it in terms of area in terms of just circumference, because all of our information was about circumference. All right, let's multiply this out. The 4's cancel. One of the pi's cancels. And so we have our equation A is equal to c squared over pi. Okay, and so where do we go from here? This is where we're probably going to have to look back at our notes and figure out how to get a differential. But remember, it's dA is equal to A prime times dC. Guess we should use lowercase c here. And we're trying to find dA. We're trying to find the maximum possible error in our surface area. Yeah, Isabella, that's right. dy equals derivative dx. Here we're using a and c instead, but Right idea? So we need the derivative. The derivative, it's just the power rule here. And now we can just plug in all the information we were given. So dA, oops. And we're taking the derivative with respect to c. That's what this right-hand part says. So dA is equal to 2c over pi times dc, which is equal to 2 times 84 over pi times 0.5. Feel free to simplify this if you'd like, but this is a fine way to leave your answer. I mean, it simplifies to 84 over pi, some irrational number. Okay, and then for the volume, right, because the next part of the question says use differentials to estimate the maximum error in the calculated volume. We're going to do the same thing, but we'll just need a different equation here. So what's the volume of a sphere? How do we get the volume of a sphere? So the volume of a sphere is (4/3 pi r cubed). Good, yeah, Jax, good. And then we'll do the same thing. So here we said r was equal to c over 2 pi. So this is where the error in my answer key appears, but we'll correct it now. So v equals 4/3 pi times c over 2 pi to the third. Why would we use the power rule for a prime and not the quotient rule? Good question. Pi is just a constant here. So if you did the quotient rule, you'd have a bunch of terms that are 0, but you'd get the same answer. So yeah, we could rewrite this as like 1 over pi times c squared, where 1 over pi is just some number. It's like a third, basically. Yeah, so we could simplify this. 4 pi c to the third over 24 pi to the third, which is equal to c to the third over 6 pi squared. All right, there's the error that was in the answer key, I believe. And again, we'll do the differential. So we need v prime. 6 pi squared is just a number. It's a scalar. So again, we'll just use the power rule here. Bring the 3 in front. The 3 would cancel out with part of the 6 here. So we're going to have c squared over 2 pi squared. And oh, another error in my answer key is it should say dv. It says dA, but fix it here. So dv is equal to c squared over 2 pi squared times dc, which is 84 squared over 2 pi squared times 0.5. Okay, so for these differential questions or like finding error, possible error, you know, sometimes you're gonna have to manipulate your equation like we did here. You know, how you kind of memorize to find the volume of a sphere was using radius. Instead, we should use circumference, but it works out to be the same. You know, doesn't really change how we're going to do the problem. Take the derivative and then plug in all the information. So are there any questions on number 11? Feel free to ask them, and also feel free to request what our next question to work on is. Yeah, we're not going to. We didn't deal with the relative error, Jax. How would you do the relative error? You would just compute the. You'd have to figure out what the surface area and the volume were at that particular time, and just divide by those numbers. So you would find what the surface area is when C equals 84. So you'd use this equation here, and you'd take our absolute error and divide by that number. But you're not going to, don't worry about the relative error because we didn't talk about that in class. I know you had WebAssign on it, but Rena says number 18. Yeah, sure. Okay, yeah, this is a hard question, isn't it? Show that something has exactly one root. So I think you picked a good one to work on. I'm gonna guess a lot of people looked at this question and just were like, I'm gonna pass. Just because remember it was a kind of a hard question when we did it in class. So let's do it now. So show that number 18. And while I'm writing it down, so we want to show something has exactly one root. Does anybody remember what our technique was for showing something has exactly one root? Yeah, we use the intermediate value theorem for part of it, and then we use the MVT for the other part. But our technique was basically we want to show it has at least one root. So just as a reminder, show it has at least one root. And we did that with the IVT. And then we want to show it has at most one root. And we use the MVT for that. Okay, so in general, right, we had on the last test, I think, we had a question that was like, show that something has at least one root, we use the intermediate value theorem. If a question asks you to show if something has at most one root, you would just use the mean value theorem. But here we want to show exactly one root, so we have to do both. Okay, and yeah, so use the IVT and then proof by contradiction with the MVT. Exactly. Okay, so I know there's a little bit of a delay here, but I think it is good to work this out through volunteering some answers. So let's start with the first part. Show it has at least one root. What's the first, we're going to use the IVT and the MVT. What is the first thing we should do in order to use either of these theorems? What properties had to be satisfied about our function in order to use the MVT, for instance? Yeah, so we should first verify that our function is continuous and differentiable. Okay, so it's a polynomial and a trig function. Both of those are continuous and differentiable. So when you add them together, they also are. So it's fine if you just write, just say like f of x is, yeah, just if you just say in words, it's continuous and differentiable, right? Because the time it's not, it's like when you divide by 0 or have some weird sort of cusp here. But yeah, so f of x so is a polynomial plus a trig function, so it is both continuous and differentiable. Okay, and so now we're allowed to use both of these theorems, right? Before, if we had a function that was not continuous or differentiable, if it was failing one of those conditions, we couldn't use the MVT. Okay, so let's start with the IVT. How do we use the IVT to show that there's at least one root? Camden, would you give us one that is not continuous and differentiable? No. No. If you had more time, I would, but I'm not that mean. No. So just just verify. Say it's a polynomial or a trig function, whatever type of function it is. I'm not going to trick you like that. Okay, but how do we use the IVT to show that there's at least one root? You would have to find a place in its domain where it switches from positive to negative or vice versa. Yeah, exactly. So I guess a good place to start is let's just plug in 0 because that's a really easy number to start with. F of 0 is equal to -1, right? Which is less than 0. And so now we need to find a value of x that makes our function positive. Does anybody have a guess? So our function is 2x minus 1. So the minus 1 makes it a little bit negative. And then minus sine of x. Again, sine of x isn't very big either. So just try to make 2x positive, and it should make the whole thing positive. So what can we use for a value? Max, great idea, 100. Really just exaggerate how positive it is. We don't want to give sine of x a chance to force it to be negative. 100 is fine. 1 probably works. I don't know what sine of 1 is off the top of my head. So maybe if you did something a little bit bigger than 1. But yeah, 100 really gets the point across. So f of 100 is approximately 200, right? 200 minus 1 minus sine of 100, which is definitely positive. Okay, so the IVT tells us, so since f goes from IVT says that f has at least one root. Okay, so that's half the challenge. Unfortunately, it was the easy half. Now we want to show that f has at most one root. So how do we do that? Does anybody remember? Feel free to put a question marks or confused face emoji in the chat, just so I could get a sense of if people remember how to do this, because I could explain it slowly if necessary. attempt to prove that there are two roots by using MVT to show that there's actually one. Yeah, that's kind of the big strategy there, Jax. So what we'll do is we'll pretend there's two roots. We'll give them names, and we'll see what happens when we try to apply the mean value theorem. Okay, so we want to let's suppose that there's two roots. So we don't even just forget what we've done the first part. Okay, I know a lot of you are going to be tempted to say, well, we know there's a root between 0 and 100, so that's one of them. Don't even worry about that. We'll just say, suppose there's two roots. We could call them A and B, or whatever your favorite letters are, and we'll go from there. So suppose f has two roots. Call them A and B. Okay, so what does it mean for f to have a root at A or f to have a root at B? So this means something. So we have a function, we're saying it has two roots. We called them f. No, we didn't. We called them A and we called them B. If they're roots, that means f of B and f of z. Jeez, can I speak? F of A and f of B are 0. Yes, Nicole. So this means f of A equals 0 and f of B equals 0. Okay, and so what we're going to do is we're going to use the mean value theorem on the interval A to B. Okay, and so this is going to be hard to type, so I'll just kind of say or remind you what the mean value theorem says. It means, if this is true that there's two roots, since we have a continuous and differentiable function, there must be a number C in the open interval A to B such that f prime of C is equal to f of A minus f of B. Sorry, f of B minus f of A over B minus A. Okay, so what's f prime of C? Well, just in general, f prime of x is 2 minus cosine of x. So f prime of C would just be 2 minus cosine of C. And what does this right-hand side become? Well, B is equal to 0. F of B is equal to 0. F of A is also equal to 0. So this right-hand side is equal to 0 minus 0 over B minus A, which is 0. So the question is it possible for 2 minus cosine of C to equal 0? And the answer is no, right? Cosine gets as big as 1. So this has no solution. And so since the mean value theorem is contradicted here, we must have broken a rule at some point along the way, and it was here. So there aren't two roots. So therefore, f has at most one root. And so since it has at most one root and at least one root, it has exactly one root. All right, and if you want to see another question that's similar to this, I made a video on it at some point. I believe it's called Mean Value Theorem, Epic Challenge Problem of Doom, or something like that. I wanted the clickbait title to get the clicks, but you know, it's calculus is just not hot on YouTube right now. Fortnite is. You know, I'm not going to be making Fortnite videos to get subscribers. I got to just do calculus. So that's where we're at. Okay, sorry. So any questions on this, or are there any other questions you want to go over? Can you explain why number 17 does not contradict the mean value theorem? Yes. Yeah, and then we'll do 19, Isabella. So we'll work through both 17 and 19. 17 is quick. Okay, so the question is, so the question is, can we apply the mean value theorem on the interval 1 to 4? That's basically what the question is asking. And so why are we not allowed to apply the mean value theorem on this interval? I guess to help point you in the right direction, what conditions do we need to have satisfied in order to use the mean value theorem? F of x is not continuous at x equals 3, which is in the domain. Exactly. Yeah. So we should have to check, you know, is our function continuous and differentiable on this interval? And the answer is no, right? So f of x is equal to 1 over x minus 3 squared. And so clearly this is not defined at x equals 3. And so that's in the domain. And so it's discontinuous. So we can't use the mean value theorem. Or it's in the interval 1 to 4. Okay, so yeah, we do have to actually just make sure, verify, you know, we're not dividing by 0 or doing anything inside of our interval. So it doesn't contradict it because we can't even use it. Yeah, and so if you tried to find a number that satisfied the conclusion of the mean value theorem, you wouldn't be able to find one in that example. The way I crafted it up is it's like just out of the interval what that number C would be. So yeah, so since the mean value theorem doesn't apply, you can't contradict something that you can't use. So yeah, that's the reason. All right, so number 19. All right, so we have f of 1 equals 10, and f prime of x is greater than or equal to 2 on the interval 1 to 4. How small can f of 4 be? Anybody have any thoughts on this one? All right, let's think. So we have this interval, and we want to find how small f of 4 could be. And we know its derivative is greater than or equal to 0 for all x in this interval. It tells us that the derivative exists at all those. Yeah, so what Jack said is right. You need to manipulate the mean, like the conclusion of the mean value theorem here. Okay, so we know that 2 is less than or equal to f prime of c, which is equal to f of 4 minus f of 1 over 4 minus 1. That's the number 2. That didn't get any better. Yeah, now we just plug in all the information that we know. So we know 2 is less than or equal to, we don't care about this f prime of c. All of our information is over here. F of 4 minus f of 1 is 10. Over 3. Okay, so we can multiply over the 3. That doesn't change the inequality sign. So we have that 16 is less than or equal to f of 4. Another way to write that is f of 4 is greater than or equal to 16. What's the smallest it could be? Well, 16. Yeah, so this is just another application of the mean value theorem. Is it gives us a bound on what the value of our function could be if we know some facts about the derivative. So I should remind you, I posted a like a practice assignment on Canvas. It's not worth any points. It's just so you could practice taking a picture of a piece of paper or maybe a few pieces of paper and submitting it as a PDF for the test tomorrow. Because for the purposes of being fair to your classmates, you're not going to be allowed to submit your test after the deadline, because you could just use more time to do math if you did that. So plan on, I'm going to give you until 11 o'clock tomorrow to submit it, but try to start focusing on submitting at 10:50. And I'll put all this in writing in an email. But you should plan on starting to try to submit at 10:50, so you have 10 minutes to figure out how to submit this thing. But I'm giving you this practice assignment so you could practice the whole situation of taking a picture and posting it to the internet. Are there any other questions about the test or questions you want to go over? Are we allowed to print off the exam? Yeah, do whatever you need to. You don't even have to write on the exam paper. If you prefer just using your own printer paper and just writing out question 1 and working out question 2, that's fine too. Submit it just like you submitted the quiz. So if you have the technology to write straight on the computer screen, that's great. That's probably the easiest. But if you prefer to write on a piece of paper and take a picture, I've been using that Adobe scanner app. It's super easy. And we have access to it through Wake Forest, so might as well use it. So are there any other questions we want to go over? Still got 10 minutes to work out some problems. Can we do number 24? We could start it. I'm not sure if we'll be able to finish it. Oh, wait, yeah, no, we should be able to finish 24. I thought this was one of the ones that's like do all 7 steps. Yeah. Oh, yeah. Let's do this. It's a good question. I'm going to just erase all this. So if you missed it, then just go back in the YouTube. Go back in the YouTube video after. Yeah. So number 24 is sketch a graph that satisfies a bunch of different properties. So I'll write out the properties, and then you can maybe use this part of the whiteboard to answer it. All right, so the properties are, so this is number 24. Okay, so f of 1 equals 0, f prime of 1 also equals 0. We have the limit as x goes to 2 from the right of our function is positive infinity. The limit as x goes to 2 from the left of our function is negative infinity. The limit as x goes to 0 from both directions is negative infinity. The limit as x goes to negative infinity is positive infinity. The limit as x goes to positive infinity is 0. F double prime of x is greater than 0 for x is greater than 2. And f double prime of x is negative when x is less than 2. I mean, x is less than 0, or 0 is less than or equal to x less than or equal to 2. Okay. Yeah, so what we should do is just start like this and just plug in the information we were given. So we have the point 1 comma 0 is on it. And we'll still have to remember about this derivative. So we'll deal with that when we finally start sketching the graphs. Okay, so we have a vertical asymptote at both x equals 0 and x equals 2. So well, we already have the x equals 0 line drawn in. Let's draw in the line x equals 2. And we know that when x goes to 2 from the right, we get to positive infinity. How do I know that? Can you clarify, Nicole, what you're asking? There's such a delay that, that could have been anything. How do I know about the vertical asymptotes? I'm assuming just because we have limits that go off to infinity at those values, if that's what you're asking. How do you know about the vertical asymptote at 0? Vertical asymptote, sorry. Yeah, because we have a limit from one of the directions or both directions going to infinity at those values. And so that's what it means to have a vertical asymptote. If the limit, as you approach that value, you go off to one of the infinities, positive or negative. Okay, so yeah, so these lines here tell us about the asymptotes, 2 and 0. Let's see, when x goes to 2 from the left, we go to negative infinity. And x goes to 0 from both directions, we go to negative infinity. So right when it doesn't have a direction, that tells us that it's both left and right. As x goes to negative infinity, f of x goes to positive infinity. As x goes to positive infinity, f of x goes to 0. F double prime of x is positive when x is greater than 2. That means it's concave up. Okay, so we just have to connect these lines, making sure we're concave up the whole time. I think that's a good job right there. And you see we're tending off to 0. F double prime is negative when x is between 0 and 2. So it's concave down, and we need to connect these two lines. So, and we need to make sure our derivative is 0 at x equals 1. We could get all those in the same go. And last is f double prime is negative when x is less than 0. So we have to just make sure we're concave down when we're connecting these dots. So we should get something like this. So are there any questions about this? You just got to make sure, and then you should just verify if you have time that we hit all the check marks. F of 1 is 0, and that's the point here. The derivative is 0 there, right? It's a local max, so its derivative is 0. And we have all these appropriate asymptotes. How do you know there's a VA at 0? I think I may have answered that, but that's from this part here. The limit as x goes to 0 of our function has to be negative infinity, which means there must be a vertical asymptote since it goes up to one of the infinities. Okay, I'll stay around and answer any questions you have about the test, but I don't think we have time to do another question. So send me an email if you have any questions tonight. I know the tutoring center will be open tonight, so you should go over there or try to Zoom in to them to ask for a little extra help if you need some help. But yeah, I'll send an email to you all some point soon, kind of explaining the details here tomorrow. Basically, plan on the test starting at 9:50, so that's when you get out of your last class. You'll have all the way to 11. It's going to be the same format as our last test. So 6 or 7 questions, whatever it was. Yeah, it stinks with the whole not being in person, but yeah, you guys will do well. Yeah, so that's all I got. Hit the like button before you leave. And yeah, send me an email if you have any questions. My brother says, great class. Thanks. Turner coming with the dankest emoji I've ever seen in my life, the dab. I didn't even know that was a thing. It's pretty sweet. All right, well, if there's no more questions, I'm going to end the stream. So bye-bye.